Imagine playing 20 questions, and your very first guess is it a 1998 Toyota Camry with a dented left bumper? That is a terrible way to start. You are wasting a guess on something incredibly specific instead of narrowing down your options. The winning strategy is to ask a broad question first, until the answer becomes obvious. This logic of repeatedly cutting a group in half is exactly what happens inside one of the most widely used predictive models in artificial intelligence. If you understand how to win at 20 questions, you already have the blueprint for understanding what machine learning engineers call a decision tree. Let us look at this diagram. We start at the very top with a massive, unsorted cluster of information, maybe a list of thousands of bank transactions. Engineers call this starting point the root node. To sort this mess out, the computer evaluates every single piece of information it has, testing out thousands of different thresholds. It is looking for the one single question that creates the cleanest separation of our data into two distinctly different groups. Once it makes that first split, it looks at the new groups and does the exact same thing again. It asks another question, makes another split, and creates new branches. The system automatically works its way downward, sorting data into more organized piles. Eventually, the algorithm reaches a point where it cannot ask any more useful questions. The data is as sorted as it can possibly be. These final stopping points at the bottom are called leaves, and they represent the model's final prediction. A decision tree is essentially an upside-down flowchart. It takes a chaotic tile of raw data and maps it to concrete conclusions through a calculated sequence of yes or no questions. Imagine a computer tells a doctor that a patient needs a risky surgery, or an algorithm tells a bank to deny your mortgage application. In these moments, you naturally want to know why the machine made that choice. Many modern artificial intelligence models are incredibly complex. They behave like sealed black boxes, where even the engineers who built them cannot see the internal math to explain how the program arrived at a specific answer. This highlights the primary advantage of the decision tree. You can actually see what it is doing. Looking at this simple flowchart, you can trace a bright, clear path from the top all the way down to a final prediction. Everything is open and easy to follow. A human expert can physically follow that exact sequence of decisions. They can see that the computer looked at an income over $50,000, then checked for a credit score above 700, and approved the loan based on those specific rules.
In high-stakes situations, being able to explain the logic behind a choice is frequently more valuable than a tiny increase in accuracy from a model nobody can verify. But there is a catch. If you let a decision tree grow without any limits, it behaves a lot like a kid who just memorizes the exact answers to past games instead of actually learning how the game is played. Data scientists call this problem overfitting. As you can see in this diagram, a tree left on its own will keep splitting until it creates a chaotic, impossibly dense map. Instead of finding broad patterns, it memorizes every tiny, irrelevant quirk in the data you feed it. Because it spent all its effort memorizing the exact details of the past, this massive tree will struggle when it sees completely new information. It will try to apply hyper-specific rules to new situations and make silly, easily avoidable mistakes. Engineers can manage this by pruning the tree, essentially cutting off the most complex branches to keep the rules simple and useful. While this prevents the tree from making wild guesses, it also limits the total potential of the model. An unconstrained decision tree trades its ability to handle the real world for perfect, useless memorization. So if a single decision tree is prone to memorizing data and making mistakes, how do data scientists build systems they can actually rely on? The solution is a technique called ensemble models. Look at this diagram. Instead of relying on one structure, an algorithm like the random forest plants hundreds of individual trees, all working together at the same time. Imagine a stadium where hundreds of people play slightly different games of 20 questions. When making a prediction, every tree casts a vote. Some will be wrong, but their individual errors average out, leaving one highly accurate group consensus. By grouping them together, the chaotic weakness of a single tree is transformed into the undeniable strength of a crowd. This specific approach is exactly what allows these powerful models to win the world's most difficult machine learning competitions. But using a random forest introduces a significant trade-off. We gain incredible accuracy,
but lose the ability to explain how the model made its choice. You can easily sit down and trace the clear path of one single decision tree, but it is mathematically impossible for a human being to trace the logic of hundreds of trees all shouting their votes over each other. This leads to a simple choice. If you are operating in a situation where you must explain the why to a human being, you build a single decision tree. If you only care about getting the most accurate prediction possible and do not need to explain the internal steps to anyone, you build an ensemble model. Choosing the best artificial intelligence tool does not come down to which math is the newest. It depends entirely on whether your goal is to simply win the game or to explain exactly how it is played.